I can fight monsters, I can't fight physics.
Hello, Ziad. So here's a question on momentum. I think momentum, yeah. So a golf ball is raised from the ground and dropped onto a hard plate to test the properties of the ball. A sensor measures the force exerted by the plate on the ball during its collision with the plate. The graph below shows a variation of force exerted on a golf ball with time. So the only formula you know with force and time, if you start off with mv minus mu over t. So that's just your Newton's second law. So Ft is equal to mv minus mu. So Ft is actually the area under the graph, isn't it? So the area under the graph is equal to mv minus mu, or delta p, or delta mv, whatever you want to call it. Okay, so show that the change in momentum of the ball during the collision is about 0.59 Newton seconds. So all you gotta do is just work out the area underneath. So you can split it into two triangles. So delta P is equal to the area of the triangle, area under the graph. So that's the only sort of knowledge point you need to remember here. And then we're just going to work it out. So in fact, it's just base times height, isn't it? So let's put that. So 2 times area of triangles, or 2, or just simply area of that. So if you put the numbers in, so you just get, I think it's a height 70, looks like 75, maybe 70, sorry, 66, isn't it? So 66 for the height times by, and the total is, in this case, it would be 7.5, because that's the halfway point, 7.5 times 10 to the minus 3. So if you put that in the calculator, you get 0.495 seconds. So that's a nice, easy start, just applying the facts. Right, so the ball strikes the plate with, sorry, it's Newton seconds, isn't it? Newton seconds, sorry. So the ball strikes the plate with a speed of, so it's hit the ball has hit the ground with 7.1 meters per second, and then it bounces back up with a speed of 3.9. So, and gives you that. Show that is consistent with a change in momentum of this. So basically work out the momentum before, okay, which is just simply mv1, if that's v1, and that's v2. Okay, so, and the mass is in grams, so convert that to kilograms, 0.45 times 7.1, and then just do the same. So that is 0.32 kilograms meters seconds minus 1, and that's the momentum downwards. And then work out the momentum after, which is mv2, which is 0.045 times 3.9. So if you put that in a calculator, you get 0.175 kilogram meters seconds minus 1, and that's upwards. And then just work out delta P. So don't forget you've got to observe positive and negative. So if you call that positive, the original direction, that is now negative, isn't it? Okay, so therefore it's minus 0.175 minus, so the original momentum, which is 0.32. So if you put that in, the minus just tells you there's been a change of direction from the original, so 0.495 Newton seconds. So, okay, so that works out all right. So let's move on to the next bit of the question. All right, so I think we 3.97.1. So the ball continues to bounce each time, losing the same fraction of energy when it strikes the plate. So air resistance negligible. Determine the percentage of the original GPE of the ball that remains when it reaches its maximum height after bouncing 3 times. Right. So they haven't given us a height, but what we do know, the GPE at the top is equal to the KE at the bottom for when you drop it. Okay, so we can work at the kinetic energy before, okay, before it hit the ground, because it's just simply a half mv squared. So a half times 0.045 times 7.1 squared. So if I work that out, so that would have been the original GPE, because that's the kinetic energy it hits the ground with on the first bounce. So that is 1.13 joules. Now, how do you work out the GPE for the second? So this is also equal to, let's put GPE 1, the first, the original. So now let's work out we can work out the GPE for the rebound, the first rebound, because you just use the kinetic energy at the bottom, its speed going up, because the kinetic energy at the bottom should be equal to the GPE at the top. So the EK, when it was 3.9, is half mv squared. So if you work that out, so it's a half times 0.045 times 3.9 squared. So I'll just put all that in. That gives you 0.342 joules. So again, that's the GPE2. So clearly, the GPE2 is going to be smaller than GPE1. So the height of the rebound is smaller. I've got the mass, I could work out the height of a one. But what I can do, I can work out the change or how much is 0.342 as a fraction of 1.13. So that you'll see how either how much energy has been lost or how much energy remains. So we can work out the percentage, that as a percentage change, let's say. So that will be equal to 0.342 over 1.13. So if you put that in your calculator, don't get the times by 100. So that is 30.3%. And that's what's remaining. So, and it says here, it loses the same fraction of energy. Okay, so it loses 69.7% every bounce, every rebound, let's say. So what does he say? So if you're left with 30.3% after the first one, what are you left with after the second bounce? You're left with 30.3% of 30.3%. And then what you're left with after the third bounce is 30.3% of that. So after three bounces, okay, you're left with, so if you did, just on the calculator, so 30.3 times 0.303 equals, times by 0.303 equals, so you're left with 2.8. So after three bounces, you're left with, so 30.3% times 0.0303 times 0.303. So that gives you 2.8% is what's left over, or you've lost 100 minus that, haven't you? So determine the percentage of the original energy of the ball that remains. So that's what remains. So only 2.8% because you're losing 30% of whatever's there every rebound. So explain with reference to the conservation of momentum the effect that the motion of the golf ball has on the motion of the earth from the instant it's released until it bounces at the plate. So when it's falling, what do we know? Well, the momentum of the ball plus the momentum of the earth is zero. Okay. So therefore, what's the momentum of the ball in the earth after? It must be zero. So therefore, when the ball hits the ground, the momentum of the ball, which is downwards, is equal to the momentum of the earth because they've got to cancel each other out, and that's going to be upwards. Okay, so this, and then after the impact, what do we know? The ball is now going upwards. Momentum of the ball is now upwards, so therefore the momentum of the earth has to be downwards. Okay, so that is a nice question of momentum.